Computer. All right. Hello, everyone. Welcome back to Complex Differential Geometry. We're back into the thick of it. And last time we were doing complex structures. So let's do a brief recap of what we've done so far in increasingly um, simplified terms. So first thing we did was, I'm still on red. Okay. First thing we did was topological manifolds. And so topological manifolds is when we still only think of them as locally homeomorphic to Euclidean space. So if they're real manifolds, then it's Rn, and if they're complex manifolds, this is Cm. And then we spent the first lecture turning those into smooth manifolds. Smooth manifolds, or C infinity differentiable manifolds. And then the next thing that we did is we looked at turning these real, so these were still real. And so the second lecture, we turned these into complex manifolds. And in doing so, we had to talk about holomorphic maps. So holomorphic maps were the analog of smooth maps to uh, complex manifolds and complex spaces. So what smoothness is to real spaces, holomorphicity is to complex spaces. And once we talked about complex manifolds, so this is lecture 2, this was lecture 1. Lecture 3, we started talking about the complex structure. Just like we got the smooth manifolds using the smooth structure or the C infinity structure, C infinity differentiable structure, smooth structure. We get the complex nature of the complex manifold comes from the complex structure. And the complex structure is on the vector space that the complex manifold is locally homeomorphic to. So yeah, we had this manifold, and you could think of it having a small patch, U, and this was homeomorphic to a patch of Cm, where M is the dimension of the manifold. And so this space is what we were adding a complex structure to, and we showed that adding a complex structure is the same thing as having a vector space over C. And we also looked at how we can go between real and complex vector spaces using a certain theorem, vector spaces. And lastly, that you can define a unique complex structure given certain conditions. Okay, so now we're on to lecture 4, and lecture 4 is about a new space. It's called a vector bundle. Vector bundles and their sections. And it's an extension of something that we've covered before. In lecture 1, we also looked at tangent spaces and cotangent spaces. And in order to extend these spaces, we end up with something called a vector bundle. There are various ways you can arrive at the idea of a vector bundle, but you could think of them as, okay, what would happen if we tried to take tangent spaces and cotangent spaces and extend them over the manifold? Um, so let's now look at what vector bundles are. Okay, vector bundles. Okay, so before we get into the rigorous definition of what a vector bundle is, let's kind of motivate what it is that we're trying to look for. So I'm going to draw this potato chip shaped manifold, and we can think of there being a point P, classic point P on manifold M. And what if, right, there is a tangent space that's attached to P, and it's called TPM. That's how we name each of the tangent spaces. And the way we think about it is that there are an infinite number of points on every point on the manifold, and there's another tangent space at each point. And so if we were to think about, okay, well, if we want to get the tangent space to stretch over the entire manifold, that tends to imply that we're going to expand the tangent space. But what we're really going to do is we're going to take the union of all of these spaces. I've only drawn a subset of them, but you have to think that this is every point on the manifold. So this will give you something called TM. And that's TM is the union, P element of M, of TPM. So every point on the manifold. This is something called tangent bundle. We'll come back to the tangent bundle a little later. But the way we can think about it is that, so we'll have to introduce this idea of fiber bundle. So let's go to a simpler manifold where this will be easier to illustrate. We have a real line, which is a manifold, or sorry, a complex. We'll think of this line as representing 1D complex space. So think of, let me put that in the same color that I had it before. So let's put it in P. So then we can think of this vector space. Let me color it in the same color. So this is that same vector space. So instead of it being TPM, we're going to generalize here. We're going to say that we're going to replace TPM with a generic vector space. We'll call it F. And this, don't confuse this with Blackboard F, which is the field. But it's we could have also called this V. This is what's called the fiber, and it's called the fiber because it kind of looks like our manifold is growing hair. And what will happen is that we're not just attaching this hair onto the point P, we're attaching it to each point. Every single point on this manifold is going to have another fiber attached to it. And in this case, I mean, in the example that we looked here, the fibers were the tangent spaces, but they don't have to be. But let's say if we fill this space with fibers, you could think that it would kind of look like this one-dimensional brush of fibers. So what happens when we merge all of these fibers together into a single space? Well, we get something like this. I'm going to shade that in on very quickly. This big space is called the fiber bundle. And since our fibers are vector spaces, this fiber bundle is called a vector bundle. Right. So this is our idea of, like, intuitively, we're kind of trying to on one hand, think about how can we integrate all these vector spaces that are attached to each point on the manifold, but also we're kind of thinking of, well, what if we attached an object to the manifold? What would it look like? And we're trying to visualize that. And together we're coming to this idea of a vector bundle. So um, we're going to now like rigorously define what a vector bundle is. So let's start with that. Let me bring it up. So it's going to be a triple. So let me write vector bundle again. Vector bundle. It's a triple E, M, and pi. And I'm going to explain what each of these are one by one. E is a smooth manifold. M is also a smooth manifold. It's our original smooth manifold. And pi is a map. It's a smooth map. Yeah, it's a smooth surjective map. Mapping uh M to E. Did I get that right? Sorry, I got that flip. It goes from E to M. And this is called the bundle projection map. M is called the base manifold because in our analogy, it's at the base of all of the fibers. So that's the base manifold. And E is the bundle space. And you'll hear people call this the vector bundle itself. This is kind of like how before we defined X tau, where X was a set and tau was a set of set of sets, or set of subsets, I suppose, set of subsets of X. And together, this was called a topology or topological space. Similarly, this whole thing together is called a vector bundle. And it maps onto what we were calling a vector bundle in our intuitive idea as well. So we'll look into this. So there are a few conditions that we have to meet in order for this to be called a vector bundle. And we'll look at that. And so one last thing is that it has these fibers of vector field F, right? F is called its typical fiber. Typical fiber. And the reason it's called the typical fiber is because this is the form of the fiber. And we'll call the fiber at each point P, we'll call it FP. FP is the fiber that is associated with the point P. In the case of the tangent bundle, this would be the tangent space. So, right. Continuing, so pi actually takes this FP and gives us back P. This is why it's called the bundle projection map. What pi does is let's say this is again our manifold, and we have a point P on top of which we have a fiber. So the job of pi is that if you give it any point on a fiber, that's FP, then pi will map it back to its base point. It'll project it down to its own base point. So we're going to need two things. One is that we're going to need an open covering, O, which is equal to U alpha. Alpha is an element of some index set. And we're going to need big phi, which is an which is a set of maps, homeomorphisms, also alpha element of some index set. So this open covering has to be an open covering of M, and we're guaranteed to have this because M is a manifold. Since M is a topological manifold, it will have an open cover and it will have a set of homeomorphisms. So condition number 1 is that let U alpha be an element of O, then we have phi alpha has to be a map from U alpha Cartesian product with CQ going to pi inverse of U alpha. So let's kind of break that down. Pi inverse of U alpha. So pi projects any point in the fiber down to its base point. So the opposite thing would be, so pi inverse would take any point on the manifold and give you back its fiber, right? Give you back the whole fiber. Any point on the fiber maps to that point. So taking the inverse map would take the point, the base point, back to every point on the fiber. But here we don't have a point. We have a subset. We have a subset of M. So what happens? So let's say that this is our open subset U alpha. That means that we get back this part of the bundle. We get the part of the bundle that is right above our subset. So that's what we're looking at. If I were to draw this in 3D for like a 2D manifold, you could think of this as there would be, let me draw it in the same color, U alpha, and there would be this tube coming out of it. This would be U alpha cross C, and what we want to say is that this maps onto the manifold. Now, notice the key distinction here that I'm going to highlight is that, let's say that I have some twisted around cylinder here. So what we need is, so this is what we would call, this purple thing is what we would call pi inverse of U alpha. And what we need is for this to be a diffeomorphism. Diffeomorphism. We didn't get the chance to talk about diffeomorphisms when we talked about differentiable manifolds, but diffeomorphisms are like homeomorphisms, but instead of preserving topological spaces, so if the domain is a topological space, then the codomain will be a topological space. In this situation, we take a smooth manifold to a smooth manifold. So diffeomorphisms preserve smooth manifolds. So, or the property of being a smooth manifold. So what that means is that we take this cylinder U alpha cross C, well, U alpha cross CQ. These are lower dimensional analogs. You're going to have to imagine that these could in general be higher dimensional objects. But so it takes this straight cylinder. This would be a prism. If you are aware of the idea of like what a prism is, this would be a straight prism with a cross section whose shape is U alpha. Its cross section is shaped like U alpha, and it can smoothly, so diffeomorphisms allow smooth deformation. So it could smoothly change into a different shape, but it couldn't, for example, have a sharp bend in it. So that's what it's saying, is that what it doesn't matter. Our fibers could be twisted around, but they still have to be diffeomorphic to the straight up prism fiber. And this is called a local trivialization. The reason it's called a local trivialization is because this object is actually something called a product manifold. Product manifold. We didn't have enough time to get into this during our discussion of real differential geometry, but we'll describe it briefly. Now it's the product of two manifolds which produces another manifold. And this is a simpler structure. Vector bundles overall are not product manifolds, but locally you can think of them as for every open set U alpha that's in our topology, we'll have we'll be able to decompose that local section of the vector bundle as a product manifold. And then we can, again, we can stitch them together the way we stitch together the manifold coordinate charts, and we can produce that global structure of the vector bundle. Okay, so number two, oh, there's another part of to number one. So they also are saying that pi of phi alpha, so this is another restriction on phi alpha, is pi after phi alpha of pz, where, so phi alpha domain is u alpha cross CQ. So this is from u alpha, and this is from CQ, which is equal to, this must be equal to P. Which, in other words, that means that if we take the pi inverse of both sides, then we get phi alpha of P comma Z is equal to pi inverse of P. But what's pi inverse of P? It's just the fiber at P, right? Because pi is taking the entire fiber down to P. So pi inverse is taking P to its entire fiber. So we're saying that this diffeomorphism with the this bundle, it needs to take each point. So this is a point in the vector field CQ, in the vector space. Sorry, in the vector space CQ. But this is the point on the manifold. So what it's saying is that if I have a fiber in P, right? When I have a fiber here, I need to make sure that all of the points of that fiber land in all of the points on this fiber, that they're preserved, that it smoothly transitions. That's what this condition is telling us. If I have, let's say I had a second fiber, I don't want suddenly for one point on this fiber to suddenly end up here on the second fiber. That would be bad. That would destroy our structure. So we're saying that's not allowed. So that's basically what this condition is trying to get at. The whole definition of a vector bundle, it's basically trying to go from a very general conception of this structure, and then we're additionally adding like constraints that make it work the way that we want it to work. So then we got condition number two. Condition number two says that, let's say that P is an element of U alpha. In that case, let's define phi alpha P of Z is equal to phi alpha of P. This is a definition. Yeah. So we're defining a different function that has the P baked into it. So the point on the manifold. So then this is a function that this function takes a point in CQ, which is this guy, and takes it to a point on the fiber, pi inverse of P. We have to make sure that this is a homeomorphism. That's what the second condition tells us to. So what does it mean for this to be a homeomorphism? Well, that means, notice that this is just CQ. If it's CQ, that means that the fiber is a topological manifold, because a topological manifold is at least locally Euclidean, so locally homeomorphic to Euclidean space. But this is Euclidean space. It's Q-dimensional Euclidean space. So this is a Q-dimensional topological manifold. Okay, that's what the second one tells us. And number three says that if P is an element of U alpha intersection U beta, and that's okay. I'm just going to do a shorthand that you're not really supposed to do. I'm going to say that that's not equal to the empty set. So U alpha and U beta are two open sets that overlap, and their overlap is not empty. So in that case, we have a function G alpha beta of P, which is equal to phi. This is going to look familiar to some of the things that we defined earlier. We're using this definition here. So this is going to be a bilinear map. Can it be a bilinear map? Well, it's going to be a matrix eventually, because it goes from CQ to CQ. So it's possible to express G alpha beta as a matrix. And so these are going to be the transition maps. And in fact, that's what these are called. These are the transition maps for the fibers. So this map, G alpha beta, has to be a smooth, complex, linear automorphism, which is a mouthful. So let's break that down. So G alpha beta has to be smooth. We already know what it means to be a smooth function. So it has to be a C infinity differentiable function. It has to be, well, it obviously has to be working over the field of complex numbers. Linear automorphism means that it goes from F to F. In this case, F is being taken to be CQ. This is partially because any finite dimensional vector space is isomorphic to any other finite dimensional vector space of the same dimension. So even if it wasn't CQ, we could say that it was a space that was isomorphic to CQ. All right. And so this also means that G alpha beta of P is an element of GL of F. That's what it means to be the linear automorphisms of F, which is isomorphic to GL, as I said, GL CQ. Or did I call it GLQC? No, I called it GLCQ. All right. So that was a lot, but that's basically what a vector bundle is. It has three conditions on it, which make sure that all of the functions that are being defined do what they're supposed to do. And so we get that structure that we talked about, where we have this manifold M, and then we have these fibers jutting out of this manifold, and they could be bent overall. So got this. And so this is E, the other manifold. And if we have a fiber on this manifold, then we can take a point down to its own base point using pi. And E m pi is called a vector bundle. This is called the bundle space. Bundle space. This is a recap of what we just did. This is bundle space. This is the base manifold. And this is the bundle projection map. And that's all you need to be a vector bundle. And then you have to satisfy conditions 1, 2, and 3. Very important. So now that we've talked about bundles, vector bundles, we can now refine our definition. There's a stronger form of vector bundles, which are called holomorphic vector bundles. Notice that everything that we did so far, the vector bundles were all smooth. So now, if we require, we're essentially requiring phi alpha p of z, or the function, the map or function phi alpha p, if this is a holomorphic map. So this is kind of like our coordinate chart for quote unquote for our vector bundle. If this is a holomorphic map, it's not exactly, that's why I'm trying to say, like, put it in the quotes. It's something that's analogous to what we were doing with the coordinate charts, but it's not exactly a coordinate chart. So if this is holomorphic, then G alpha beta is, which is a map from U alpha intersection U beta to GLF, or which is isomorphic to GLCQ. Then this is also holomorphic, right? Because it's a composition of holomorphic functions. Holomorphic. So that's a holomorphic vector. Everything else is the same. We still have E, M, and pi. We just require this set G alpha beta to be holomorphic. And if it's not clear, G alpha beta are the set of transition functions that allow us to go, let's say I have a U alpha here and a U beta here. So this is the top view technically, the way we've been drawing these vector bundles. We're viewing it from the top. So this is M, let's say. So let's say I have a fiber that's over here, right? We could describe this fiber in U alpha's coordinate system, and we can describe this fiber in U beta's coordinate system. And G alpha beta is the transition function that transitions the fiber from U alpha's coordinate system to U beta's coordinate system. That's actually what's happening. And it makes sure, and this whole thing, smooth, complex linear automorphism, makes sure that when we're moving from U alpha to U beta's coordinate system, that the fiber doesn't get ruined on that transition. Just the same way that we were thinking of the transition maps of our coordinate chart, and we didn't want to ruin the differentiability properties of a function when moving coordinate charts. So similarly, we're doing something of the same principle here, which is why they're also called transition maps. Okay. So we're now ready to talk about the next thing, which are sections. Sections on vector bundles. So this is kind of like the way I like to think about this is that there is a logical progression of ideas with vector bundles. And the next thing that we could do is that, so we've taken all the vector spaces that are in all of the parts of the manifold, and we've made this big union of them, and we put them all together, and we call that union the vector bundle, right? So uh, let's say we have this manifold M, and we have a bundle on top of it. Make it curved in general. That's our bundle. And let's say that we cut, like we just literally, we take a knife and we cut a continuous section out of this vector bundle. And I'm gonna try to make sure that this looks like it's not a smooth cut for reasons I'll get into shortly. So let's say that this is the kind of cut we made. We like cut it along a little way. We slanted our knife upwards. We cut up and then we continued cutting horizontally. So you could say that this is a continuous uh, cross section, kind of the idea of a cross section. So this kind of informs our idea of what a section on a vector bundle is going to be. So let's again take one of the fibers and notice that this fiber will intersect with this section at some point, right? But what is this fiber? It's actually a vector space. It's a vector space F. So this, so if the vector space is the entire line, then a single point, let's say this point, that point is a vector, right? The point is an element of a line. So the point being an element of a vector space, it's a vector. So this is a singular vector. And what it means, and since we know that every point on the manifold has an associated fiber, we know that each fiber is going to intersect with that blue surface at some place. And we're going to choose one of the vectors in that in the manifold on every point using each of the points on the section. So what I mean is, for example, there's another fiber, and that fiber gets a vector chosen with this section as well. And you can think about every single fiber on the manifold, the cross section will cut through it somewhere, and that will choose a vector on that manifold. So, or a vector at that point on the manifold. And so what we end up getting is a choice of vector for each point on the manifold. Now, think about what would happen if our manifold, for example, was R2. I'm going to use R2 because my tablet screen is a subset of R2. Or C2. Or you could say that this is C1. C1. Let's say that what happens if I choose a vector? So like let's say that this was a tangent space, right? So then we would choose a tangent vector at each point in the manifold. If we did that, what do we get? Well, this looks an awful lot like a vector field. It's a choice of vectors at each point on the manifold. In this case, the manifold is C1, but C1 is isomorphic to R2 in the sense of being a vector space. So we end up with what we would call a vector field, but what properly would be called a tangent vector field. So this is an example of what a section would look like. Okay, so what essentially is a section? Well, this just kind of tells us it's like a choice. It's a choice of vector in a continuous fashion. So notice that this has to be continuous. It's a choice of vector at each p element of M. So how do we choose something? The way we choose something is we use a function, and the function's output for each point will give us the choice, right? So we need a function, let's call it S for section. And so if you give me a point on the manifold, so my domain is the manifold, then I will tell you which point in the fiber I am assigning to that point on the manifold. And the union of all the fibers is the vector bundle, and where like the bundle space is basically what encodes most like that space of the vector bundle. So it's a function that goes from M to E. But it is subject to a similar condition as the ones we've been looking at before, where this function, pi after s, has to equal the identity map on M. What does that mean? It's a very similar thing to one of the, I think, condition number 2 that we were looking at before. Pi after s means that once we take the section, if we were to take this vector here, pi needs to be assigning it its own base point, right? So if I'm given a point P from M, then I can't assign it a point, a vector outside of it. So I can't assign to P this point, because then if I took pi, then I would come down here, right? So basically what it's saying is you're only allowed to choose, because I gave the function too much freedom, right? Because I allowed it to be anywhere on E. But anywhere on E is too free, because I could take it over here. I could even take it not on the section at all. I could take it over here, right? I mean, I guess then the shape of the section would be different. But I could put it over here. I could put it over there. But that doesn't work because I want to attach to P something from TPM or something from FP, right? In general. So if this is FP, it's actually FP, then I want to assign to P a vector from FP. So this condition is basically telling me that P must be assigned a vector from FP. That's all. But also that every P in M, every point on the manifold has to be assigned also. So each of them has to be assigned, but they all have to be assigned. And so sometimes you will see this being called a global section. You can call it a section, you can call it a global section. This is going to contrast with what we're going to talk about a little later, which is called a local section. And so you could call it a global section if you want, because it spans over the entire manifold. And the section is smooth if S is a smooth function. Smooth function. So in that situation, you would get, let me draw that in a different color. I haven't used yellow. Then your section would look something like that. This diagram is getting a little busy, admittedly, but let me shade it so that it's more highlighted. Notice that this is a smooth surface, so this would be a smooth section. Smooth section. And just like with, so when our vector bundle is a holomorphic vector bundle, then we can also make the section a holomorphic section. In order to make it a holomorphic section, all we need to do is we need to make sure that S is a holomorphic map. And what does it mean for it to be a holomorphic map? Well, S preserves the complex differentiability. So instead of it being smooth, instead of it being real differentiable, it's Holomorphic, which means it's complex differentiable. Okay. So our next thing, this whole lecture, we're defining a lot of new objects that we're going to use later. So this is kind of like an interim uh, an interim session where we're kind of building up to some of the things, some of the results we're going to get later on. But we need to understand what vector bundles are in order to discuss some of those things. So yeah, so just like we had global sections, we have local sections. And remember, we're working on a topological manifold, right? On a topological manifold or in a topological space, you have these things called local neighborhoods. So if I draw the manifold and let's say that this is my open set, which is my local neighborhood, U alpha, local neighborhood, then we can think of, let's say, restrict the bundle to just the part that's above the local section. Or just, I have to not say section because section is the name of the object. The local subset, the local neighborhood, just above the local neighborhood, the part of the bundle that's right above there with all of its fibers, many, many fibers, this is called the local section. Sorry, this is not the local section. Sorry. This is, I would call this the restricted bundle. I don't think it has an official name. There's one more step to get the local section, which is we actually have to take a section out of this. We took a section out of this. It's not very visible. I'm going to erase some of these bundle fibers to draw this. So if we took a section out of this section would be called a local section. Local section. As opposed to a global section, which it's not defined over the entire manifold. Now, these are interesting because one thing that we can do with these is we can make something called a local frame field. This is the last thing we're going to be talking about today. So a local frame field is essentially just a set L of local sections, where S alpha is very important, linearly independent local section. And what does alpha range over? Alpha ranges over 1 to Q, where Q is the dimension of the fiber. Okay, the reason I said O is I forgot to talk about what Q is this entire time. We were talking about CQ, remember? So let me say it now. If we use CQ in that definition, for example, U alpha cross CQ, Q is what we call the dimension of the vector bundle. So if I say Q dimensional vector bundle, I always forget to talk about the dimensionality. I did that with the manifolds as well. So apologies for that, but yes. So a vector bundle, the dimension of the vector bundle is the dimension of the vector space on the fiber, or that represents the typical fiber of that vector bundle. So even if the manifold is an m-dimensional manifold, like this M is a small m-dimensional manifold, the vector bundle is a q-dimensional vector bundle. So when we want a local frame field, the dimension of our vector, it needs to have as many of them as the dimension of our vector bundle, as in the dimension of the vector spaces on that vector bundle. And what is this? So local frame fields, it sounds like this completely new thing, but it's essentially the same principle as what we've been doing the entire time, which is we've been taking something that is locally defined at a point P on the manifold, and we were saying, okay, well, what if we took all of the spaces that are attached to every point P and we aggregated them together? If we did that globally, we would get a global object, and if we did that locally, we would get a local object. In this case, it's a local object. So what is a local frame field? Well, if we took some open set U, right, U alpha, let's say, and we took a section, um, so, right, so there's a bunch of fibers above this, right? So each of these fibers is a vector space, and vector spaces have something called a basis, right? We're all aware of what a basis for a vector space is. This entire time we've been talking about vector bundles. The important objects are the vector spaces. So we can do this turning one basis into the basis for things over the manifold, over a local section of the manifold, for bases, right? So what happens if we take the basis for one vector space at a point P, and then we extend it to include all of the bases in all of the fibers on over all of the fibers in U alpha? Then we get a local frame field. So um, so we take a bunch of local sections. So a local section is a choice of vectors, right? It's a choice of vectors at each point P. So we take a bunch of linearly, that's why, by the way, that's why it needed to be linearly independent, because basis vectors have to be linearly independent. So what happens if we take a bunch of vector fields, right? These are what the sections are. They're vector fields. So what happens when we take a bunch of vector fields and we say, well, they have to be, well, these are pointwise linearly independent, pointwise linearly independent vector fields. That what happens is that if let me draw this a little bit bigger so that we can visualize this better. M U alpha. So let's say I have this bundle. I'm not going to draw the insides this time. So let's say I have a section like that. I have a section like this. They can't intersect each other because if they intersected, they wouldn't be linearly independent. You can think about why that's true. So you can think that there's like this fiber here, right? It's going through all of them. So it intersects the blue section, it intersects the red section, it intersects the orange section, and produces three vectors. So let's say that in this situation, Q is equal to 3, right? So what these three actually represent is three vectors, right? Let's call them V1, V2, V3, or better, let's call them E1, E2, and E3. This is a basis. Because these have to be pointwise linearly independent, this is actually a basis at that for this fiber FP, right? So, and the sections basically choose three vectors at every point above this purple set U alpha. So by choosing these linearly independent local sections, we're essentially choosing a basis for every fiber above that above that open set. So that's what a local frame field is. It's a choice of basis for every point in that open set, that local neighborhood. So we're going to cap this off by talking about an example of the usage of local frame fields, because I think this will be illustrative, because it seems like where would we use this? But we actually do use this. This is actually used in general relativity, which is an application of differential geometry. So in GR, we have something called the tetrad formalism. Tetrad formalism. And we use the tetrad formalism to express something called a tensor. We're going to talk about tensors in the second half of this lecture. Um, in something called a local frame. In physics, one is very familiar with this idea of local frames, but a local frame is actually in math a local frame field. So here, the local frame field L, we're going to call it L tetrad, is equal to this. I'm writing it a little bit differently from the notes just to illustrate my point. So these are all local sections. Right. So you got STA, SX. I'm not going to pronounce the A. SY. These are all small s's. So SZA. These are the basis vectors. They're time and the three spatial basis vectors. This is on something called a Lorentzian manifold. We haven't looked at Lorentzian manifolds yet. They're kind of cousins of Riemannian manifolds. And so these are 4D. So they will have 4 basis vectors. And so these sections choose basis vectors over like a local patch of space-time. So this 4D space is space-time. And it allows us to talk about these tensors that are working in this overall curved space-time. And talk about it in a more simple manner. A lot of these symbols that I'm going to write now are going to make more sense later on in the course. But for people who are already familiar with the tetrad formalism, this is going to, sorry, I wrote E in the notes. I'm trying to switch that out. So this will be maybe a bridge to understand where this is coming from. So this is called the metric tensor. Metric tensor. And so this is defined to be S mu A, S nu B, eta mu nu. And I'm going to explain all of these symbols. So, and we define this to be eta A B. So, okay, so we know these are the local sections. Local sections. And we know that this is something called the metric tensor. I won't get too much more into that. This is something called the Minkowski metric. This is the tangent space. The Minkowski space is the tangent space to the Lorentzian manifold. And let's go over what these indices are. So mu and nu are called space-time indices, and they run over 0, 1, 2, and 3, which correspond to each of these. So t is 0, x is 1, y is 2, z is 3. And A and B are called local indices. Local indices. They're A and B both run from I guess you could say 0 dot dot dot, or we could start from 1 actually, it doesn't matter, dot 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 q. Because they index into the vector space of the vector bundle. So there you go. This is one of the places where we use local frame fields. Okay, so that's what we wanted to talk about for today. And if you want, you can get into where local frame fields come from, a little bit more from the other direction. I know we didn't talk too much about fiber bundles today. We just said that, okay, think about fibers on this manifold, and then we quickly transition to those fibers being only vector spaces. But in general, the fibers could be a set and a different kind of set other than a vector space. And if that's the case, then we get different kinds of bundles. If you want to read up on that, page 122 of Chernchen and Lamb has a lot of stuff uh, on specifically this bundle that we're interested in here, which is called a frame bundle. A frame bundle is kind of a collection of it's a bundle where the points themselves are collections of sections on the main manifold or the main bundle. So the sections of the frame bundle are local frame fields. So if you want to read up more on how that works, then you can look at Chernchen and Lamb. And yeah, so that is it for today. We will conclude with a brief summary of what we did so far, which is we defined a bunch of things. So summary. So number one, we defined a vector bundle, which was E M pi, where E is the bundle space, M is the base manifold, and pi is called the bundle projection map. And we also looked at something called, let me just draw this out real quick. If this is E, then we saw that it could have this thing called a fiber. This is its typical fiber. And we have a map pi that maps any point on that fiber down to its own base point. And then we looked at some conditions on the maps that are involved in the definition of the vector bundle so that it is completely consistent with what we expect. Number two, we defined holomorphic vector bundles. Holomorphic vector bundles. Then we defined sections, global sections, which ended up giving us these the mathematically rigorous idea of what a vector field is. So global sections. Then we looked at, let me go back to see what it was. Holomorphic sections. Holomorphic sections. And then we looked at local sections. And then we looked at how we can stack local sections to make sections of basis vectors called local frame fields. And we looked at an example of the usage of a local frame field in something called the tetrad formalism. So that's it. Next time, it's lecture for continued. We're going to look at tensor algebras, or sorry, we're going to look at tensor spaces. and we're going to look at some tensor bundles. Because tensor spaces, confusingly, are vector spaces. Even though tensor spaces contain vector spaces, question mark, we'll think about that next time. You might be able to figure out what the problem is in that statement that I made. If you've been observant about what I've been saying about tangent vector spaces recently. So these are a form of vector bundle, and we're going to be looking at them, and we're going to need to know about the tensor bundles in order to talk about some of the things later on. So that's why we're talking about these. But from these tensor bundles, we're going to get tangent bundles that we've been hinting at from before, tangent bundles, and we're going to get cotangent bundles. All right. So before we conclude, if anyone has any questions on what we covered today or in a previous day, something that didn't make too much sense, or feel free to ask. I'm going to quickly have a drink of water. Okay, it seems like there aren't any questions, so let's end it here for today. Thanks everybody for coming. See you next time when we're going to be talking about tensor spaces. All right. Goodbye, everybody.